It is a pleasure to welcome you to the 5th edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The International Workshop on Biogeotechnics was hosted in 2024 during the 5th edition of the AGERP lecture series. The following lecture on Reclamation and Ground Improvement on Soft Marine Clay was delivered by Engg Kumar Pitchumani at this workshop. Dr. Kumar is a Regional Director at AECOM India Pvt Ltd, heading the Geotechnical Engineering business line and involved in the analysis and design of the geotechnical components of large infrastructure projects. He brings in 32 years of professional experience in the field of geotechnical engineering, encompassing teaching, research, consulting, analysis and design in various aspects of geotechnical engineering. His experience includes foundation designs for various types of structures in the transportation and marine infrastructure projects. He has been responsible for various projects involving ground improvement of soft clays and reclamation fills. Dr. Kumar did his bachelor's in civil engineering at VJTI Mumbai in 1987 and then his M.Tech and PhD in geotechnical engineering at IIT Kanpur in 1989 and 1982 respectively. Prior to moving into the industry, he started his career with National Institute of Rock Mechanics and then as assistant professor at IIT Madras. Since 1999 he has been in the consulting industry with L&T Rambal, L&T ECC and COWI before joining AECOM in 2011. He has around 40 publications in journals and conferences. 4 of his papers have won the Best Paper Awards constituted by Indian Geotechnical Society. In the year 2022 he won the IGS Leadership Award for contribution to professional practice instituted by IGS. He was also an adjunct professor at IIT Madras and is visiting professor at NIT Trichy, disseminating his industrial experience to the student community. He is a chartered engineer with the Institution of Engineers, London. Outside his professional career, Dr. Kumar has a passion for well-being and teaches aspirants various breathing techniques to boost immunity and health. He also takes interest in treatment of chronic diseases through alternate systems, without medication.
So thank you everyone. So let me go ahead with my presentation. This is one of my favorite projects I have done. You will just see everything in geotechnical in this project as far as soft soil is concerned. I have a small video at the end. Yeah, so now what I am presenting is a Google image. So this is and we are going to look at a ground improvement project which is for Jawaharlal Nehru Port Trust. So as you go down, so this whole thing is Jawaharlal Nehru Port Trust, this whole area. Okay, so this is Mumbai. You come by boat or now this connectivity is there, which is your MTHL or Atal Bridge. Even I have been involved in this bridge also. I was involved. Now this is the project under consideration. This whole thing is Jawaharlal Nehru Port Trust. This is BPCL terminal. This is terminal 1, terminal 2, terminal 3. Okay. And this is the terminal 4, which I am going to talk about. Okay. So let us go further inside. This is terminal 4, which I will say I have built it from scratch. So if you see here, this is a jetty. Now this is operational. I am showing you on Google Map, operational. So this is the terminal 4. So this length is 1 kilometer and this width is around half a kilometer. And this is the railroad track which goes around 4.4 kilometers. Okay. So this whole thing is reclaimed area. Now let us go to my presentation. So this is the presentation. Okay. Is it clear presentation? Visible?
Yes. Yes.
Okay. So it's reclamation and ground improvement on soft marine clay, or I can say reclamation on and ground improvement of soft marine clay if it had to be written very clearly. So this is the same site. You can see this, the same thing. This is during construction. So one of the photographs which I have taken during construction, this is all during the reclamation process. So this whole area you see here, this is where that jetty is. Now which is the jetty will be somewhere over here. Okay, now before construction, And this whole thing is reclaimed area. So this is an intertidal zone. This is the existing Jawaharlal Nehru. This is the BPCL terminal. This is the BPCL jetty. Now, what is it that we require? So that is the main question. So this is the final handover product. You see this, I'll explain this to you. So this is the reclamation. The average seabed is somewhere around +1. So it varies between -1 and +1. On this, we need to create a fill. The existing terminal is at +7. The terminal which we saw adjacent is all at +7. So we need to raise this to around +6. And then on top of that, the railroad corridor, all that will come and finish it off at around 6.5 or +7. Okay. This is the final cope line. Or this is the final, we can say, you call this as a cope line, beyond which this slope is there. Okay. So this is what we need to produce. This is the final handover product. Okay. That is during its operational, this has to be, the final surface has to be at +6 +0.5, which is +6.5. That means it should not take any more settlements. Now look at this. This is what it was. Okay. Now this same thing, I'm presenting it slightly differently because when I put my investigation and all in my drawings, this is how it looked. Okay. So this is that 1 kilometer width container. This is a ½ kilometer of the container. And this is the railroad corridor. So if you see here, there are some 89 boreholes. We did some 63 cone penetration tests, then cone dissipation tests, field vein shear tests, radial consolidation tests, and laboratory tests for the consolidation parameters. Look at all this. These are all various legends. You have what we did was there were some tender boreholes. So we had new boreholes. So we named some various numbers and various legends we gave for different types of boreholes. Now this is how the strata looks. Now look at the strata. The top layer, this is that +1 level, -1 level, somewhere. So average is some +1 over here. This whole thing is unit 1, which I am describing here as very soft to soft marine clay, where the SPTs are in the range of 4 to 8. In fact, they are even lesser. 0 to -12. So 0 to -4 is very soft clay, and -4 to -12 is soft marine clay. And it's followed by a very small layer of residual soil of basalt. Okay, so this is the whole profile. You see some SPT values. So some of you will ask question, why are you doing SPT when it is soft clay? That is why we had done a lot of CPT tests. So all this is from before the during the tender stage, those SPT. You see that these values are extremely low. Now look at this. This is that again the container, 1 meter long, ½ kilometer, 1 kilometer here, and this is a railroad corridor. This shows the thickness of clay. This dark red is almost 20 to 24 meters. So this portion is almost 20 to 24 meters. It drops down drastically over here to around 8 to 10 meters. And then it drops down to around 4 meters over here. And when we went back, it again went down to some 10 meters. So there is a large variation. So the rock profile is something like this. Okay. Now what we need to do? On this profile, we need to reclaim. Correct? The final profile, what we need is a surface at +6. So definitely we have some 20 to 25 meters of very soft clay with SPT values less than 4 and 8. Soft clay is there. So definitely there is going to be lot of consolidation settlement, bearing capacity failure, shear. How am I going to construct? So that is the biggest challenge. You see the liquid limit somewhere around 100, 80 to 100. See this green spots? So 70 to 110. So average around 80 to 100 is the liquid limit. Natural moisture content, very close to liquid limit. Look at this, somewhere close to 80 on the top. So the top soil is almost like normally consolidated clay. If Professor Madhav was there, he will not allow me to use this word because it's a misnomer. We can deal with that a little later. So it is very, very soft clay. You see the plasticity index, again in the range of some 40 to 60. So highly plastic CH soil. So what will it do? It will settle. Lot of consolidation settlement. SPT value is very, very low. Now look at this. Now look at, these are various plots. This green is definitely the CPT. This green is a CPT plot. Now look at the CPT values over here. It is even less than 5. Look at the CU value over here. It is less than even 5. Somewhere around 2 and 3 are the values of cohesion values. Look at this very soft clay. 0 to minus 3.5 is just around 2. And soft marine clay before minus 3.5 to 5. You have this profile we can take, and beyond that a stiffer clay is there. Okay, these black points are all from vein shear tests. So if you see here, so how do we do the design? How do I go ahead with the design is the biggest question. So what we came up with is not an average. We came up with a 25th percentile line. Okay, so this red color spot line is a 25th percentile line. That means 75% of the points are above this line, 25% of points lie below this line. And ultimately we took this as the design line, which is the black line, which is slightly or somewhere closer to the 25th percentile line. Okay. Now look at this coefficient of consolidation, CV values, just in the range of 1. Okay, CV of 0.8 to 4.5, others were there, but predominantly it is close to 1. Okay, then you have coefficient of radial consolidation, CH. So now this test we did in the IIT on, we collected some very good undisturbed samples, almost 100 mm diameter. We collected those samples, retrieved those samples and did radial consolidation tests at IIT Madras. And that came in the range of 1.9 to 4.25. So this is what we got from the laboratory test. Then we did some cone dissipation tests also. Here again, the CH is somewhere around 246 in this region, meter square per year. Okay, so CV is somewhere around 1 meter square per year. Now look at this compression ratio, which is CC upon 1 plus E naught. Look at this 0.2 to 0.3, which means it is very, very high. Compression ratio is very, very high, somewhere 0.2 to 0.3. Okay, now this is C alpha. Look at these values. C alpha also lies between 0.015 to 0.035. So this is for primary consolidation. This is for secondary consolidation, which are again very high. Then we plotted this, which is the primary consolidation index CC, which is C alpha by CC. We got a very beautiful line, which is the C alpha by CC is 0.033. So this was a very nice plot we got. Now look at this OCR. OCR is between 2 and 5. See this? Where did this OCR come from? So that is the big question. On sea, which is a tidal belt, you have an OCR of 2 to 5. All this is because of tidal variation. Lot of water coming in and out and desiccation and wetting, all this put together has created this OCR. So you might rather say that this is some over-consolidated clay, but the SPT values are very low. So how will this clay going? How is this clay going to behave? See, these are again parameters which I have already shown you, that it is CH soil, extremely compressive. See, CC upon M plus E naught is 0.2 to 0.3. CV is around 0.8 to 1.7. So based on this, we came up with design parameters. So these are the design parameters. So what we did was, see, there is some variation. Okay. And the area is also very large. So what we did was, we broke this down into number of zones. You can see here, various zones are over here. Zone 5, 4, 3. This is zone 1, 2, 3, 4, 5. Here there is one zone 6, zone 7. All this we did depending, looking at the thickness of clay. So if you see here, the thickness of clay was almost around 20-24 meters near zone 5 and zone 6. Zone 4, the thickness of clay was around 10 to 12 meters. Zone 3, the thickness was just around 8 to 10 meters. Zone 2, 4 meters. Zone 1, again around 4 to 5 meters. So that is how we distributed the whole area into different zones. So in these different zones, we took the tests that were available at those zones and took the design parameters based on the tests available in that zone. Okay, so in each zone you will have a slightly different parameter adopted. Now you see what is going to happen. I have not shown the graph. You will see it slowly. There is a seabed. We need to raise it to some level. Consolidation is going to take place. We have to do some ground improvement. How will you do ground improvement? Unless you raise this to a certain level above water, you cannot do ground improvement. That means that level was somewhere around plus 5.5. So up to plus 5.5, you have to dump. So what will happen is you have to dump. After that only you can do PVD. Then what will happen? You have this embankment, and at the end where you have an edge, correct? So this edge will undergo soil slope stability failure. So during construction itself, you are creating an embankment. You are creating small portions of a bund, an embankment, keep filling. So you always have a slope. So this slope has to be maintained. So that is why in slope stability analysis for the perimeter bund or the entire, wherever there is a slope, the temporary condition is during construction, factor of safety should be 1.3. During static case, the factor of safety is 1.5. This is the permanent condition. So permanent condition is after I do all my ground improvement, I remove all the surcharge, come back to my plus 6.5. At that time, if I do analysis, it should be 1.5 in static case and 1.1 in seismic case. But during construction, it has to be 1.3. So this is the biggest challenge. Settlement analysis, I need to hand over at 95% consolidation once my temporary construction is over. Then when the permanent thing is, when I come to the permanent position, which is at plus 6.5, 95% consolidation should have been over for all the loading that is going to come. And the residual settlement should be less than 100 mm for 2 years, less than 150 mm in 5 years, and less than 300 mm in 20 years. Okay. And deformation analysis of the edge structures for this one, we fixed it as 25 mm vertical and horizontal around 75 mm. So these were the conditions that were applied. Now, how do I go about constructing this? Okay. So as I keep doing, so this is how I will do the construction. See, this is the soft marine clay. Then I have this reclamation bund, which I am going to construct. On top of this, there is going to be one surface on which the container stacks will be there, then railroad and rail corridor and the road corridor. So the loading from the container stacks is 50 kPa, from the rail is 30 kPa, and from the road is 10 kPa. These are all revetment. Okay, don't go by the slope, it looks a little steep. So these are the design requirements. See, the soft marine clay varies from 5 meters to 18 meters. CU is 5 to 7 kPa up to the top 2 to 5 meters. Such soft clay, you can imagine. So how is the construction sequence? This is the +1 level, 2.5 is the water level. That is the mean sea level, average water level. I raise this to plus 5.5, which I have to go beyond the water level. Then I put drive PVDs. Then I have to raise it in layers. Now, what is the final surcharge I need? We need to calculate. So whatever be the final surcharge, it cannot be put in one go because the slope will fail. So I have to go to say +8, and then I have to go to the final level of +12. Okay. I wait here until 95% consolidation is over. Then I will remove this, remove the surcharge, remove everything, and then come to the final 6.5 or 7 level and hand over. Okay. This is going to be my construction sequence. Now look at these parameters. This is in one of the cases. As I told you, different zones have different parameters. Now look at this. Here it is somewhere around 7 kPa. So 7, this is how the shear strength increases, and this is how the gradient we took in one of the cases. Okay. So the unit weight, all soft clay. So with this as shear strength parameters, we go ahead with the design. Now, what are we going to do? As I said, we have to first go and dump. Correct. Unless I reach to plus 5.5, I will not be able to do any ground improvement. Or you have to do marine-based ground improvement, but the time it is a shallow water zone, tidal zone. Most of the time the land is there. Within 6 hours the water will come in. So I cannot do marine mode of ground improvement. So I have to fill it somehow. So when I fill, what will happen? Since the top layer has got such a small cohesion, which was around 2 to 5 kPa, what will happen? The whole thing will get washed away because of bearing capacity. If you do simple bearing capacity calculation, even beyond 2 meters, you cannot fill this. So look at this figure over here. After we did the filling and took it up to 5.5 meters, this is how the whole thing was. See, before filling, the ground was at +1, okay, which is the soft clay. After filling, I did a borehole to check where that soft clay is. The soft clay had moved here. That means from -2 to +1, which is almost 3 meters, 2 to 3 meters, the whole soil has been replaced with this fill. So where did that soil go? Where did that soil go? That we'll see now. So that is what is here. If you see on top, the soil is a better soil. The top 2.5 meters got filled up with better soil, which we got through confirmatory boreholes. And the cohesion CU was somewhere around 15 to 25 kPa. So this is what happened. Look at this. This brown color is all the fill soil, and this black color is all the foundation soil. So what has happened is, as you fill this, the mud has waved. So it's typical bearing capacity failure. So this has gone down and it has pushed the clay out, and that clay is what is spread all over this place. Look at this. All this is black. This whole thing black is all the mud wave. Okay. So this is called mud wave. So you see the levels, this has gone up to +5.5 and the mud wave is also at around +4 or 5. That means 4 meters of mud has given up. Okay, so some parameters for geotechnical analysis for the reclamation fill, these are simple things, what shear strength. So once we come to +5.5, we did the ground improvement using PVD. Okay, PVDs were inserted. Now, how do I, after the PVD is put, how do I raise it to my final surcharge level? Because failure will take place, no? So what we did was, now look at this. From seabed to +5.5, I need a CU of 13.5 for it to be stable. Now most of it has got washed away by this one. I wait for the PVD to consolidation to take place. In fact, it may not take place because it will need some time to start. But at that time, I had 13.5, so that was stable. Now from 5.5 to, if I have to raise it to +7 or 8, I need a CU of 26 kPa so that I get a factor of safety of 1.3. See, that was a driving condition. So what I have to do, I have to wait till 50% consolidation. So this waiting time was 15 days. So I will wait at +5.5 for 15 days so that I can raise the surcharge from 5.5 to 7. Then what I do, from +7, if I go to the above +8 or +12 or +10, depending on the loading, I need another 20 days waiting time. That means 70% additional consolidation. I need 34 kPa. So I will wait here for additional 20 days, do a borehole, check, or I'll do a CPT to check if I have achieved 34 kPa. After that only I can raise it to the next level. Then finally I go to the permanent condition, 95% consolidation. So I have to wait at the final level for 90 days, which is around 3 months to finish 95% consolidation. That is what is this. And I will achieve a CU of 56 kPa. Okay, so this is how I have to do the stage consolidation, stage construction, looking at the factor of safety of 1.3. So these are all the PVDs that were done. We did some slope stability analysis. As I said, temporary condition, I need factor of safety of 1.3. We used slope W software, Morgeston price method. We used circular and non-circular slips. We considered all cases to see how the factor of safeties were. Now, what we discovered was we need layers of geotextile, at least 1 or 2 layers of geotextile above +5.5 to take care of the temporary case, not the permanent case. In order to achieve a factor of safety of 1.3 during construction, I needed geotextiles. Okay. But in the permanent condition, geotextile was not required. You see the slope stability analysis. This at this level, we need to put the at +5.5, there are layers of geotextile, either 1 or 2 layers of geotextile. Now, what you have the slope, this slope should also not fail tomorrow, isn't it? That means 95% consolidation has to take place below the slope also. So how do I do? So I have to overfill. Beyond the scope line, I have to fill this by at least 12 meters away from the scope line. See this 12 meters extra fill I had to put and then take a slope so that I can take the PVDs right up to this edge, so that this entire slope which will end over here is 100% or 95% consolidated. I hope you are understanding. So these are the different layers. We took the mud wave also into account to take care of giving me sufficient protection. So like this, we did various slope stability analysis for all the stages, for all the zones, came up with a scheme of how much waiting time is required in each of these zones and how much of this overfill is required. So in this case, this overfill was around 12 meters. In some other case, the overfill was almost 25 meters, depending on how soft the clay was. Okay. These are various slope stability analysis that need not go into details, but we had to do this analysis. So in summary, after we did all this, we have to cut back this 12 meters. That overfill that was done, see, this is the overfill. This is where the revetment will actually be. The final surface will look like this. Look at this red color, that is the tension geotextile. So I have put everything in one picture, the temporary case and the final case in one picture. So all this portion which is beyond the cope line. See, this is the cope line. Beyond the cope line, whatever is there, all this material, I have taken it out. After all the consolidation and removal of surcharge is done. So we have to dredge out all this so that my final figure is available. Now let us see the settlement analysis. So these were the various values which I showed for considering this one. So we envisaged a settlement of around 1.5 to 2 meters. Okay, over a period of 2 years. So now suppose I want a surface at +7. And I assume that there is a settlement of 2 meters that is going to take place. So 7 plus 2 is 9. And then I need a surcharge to take care of the future loading that is going to come, which is 50 kPa. So suppose I take a density of 17 kilonewton per meter cube, 50 divided by 17 is 3 meters. So I will need 3 meters surcharge. Correct? So what I need, you have 2 meters of the settlement and 3 meters of that surcharge, which is around almost 5.5 or 6 meters. So beyond the 6 or 6.5, I'm going to put that 6 meters, which is what that 12 MCD is. Okay. So approximately I need to put surcharge up to +12, wait, and then remove it. Okay. The contract site handover was around 240 days, which is very, very tight. So now look at the CH values, rate of consult. Now, what we did was we compared the lab and field data. We compared the radial consolidation and from cone dissipation tests. Okay. And then we did ground improvement, which I told you now in triangular pattern. Various surcharge loads were say +10.5 and +12. 95% consolidation had to be targeted. Okay. Now PVD, all this you know, we did the PVD and all this you know how PVD works. So I'll not go into this. Then we had to do a lot of instrumentation. How will I know when I should take the surcharge out? So we had to do Asoka's method. So this is what various instruments we have done at +5.5. See, look at this: magnetic extensometers, vibrating wire piezometers, inclinometer at the edge, and then settlement gauges. All these were used for back analysis and continuous monitoring. And how are they placed? At every 25 meter spacing. So look at this. This is how the spacing, this is how the instruments all look like. So this is how one plan I'm showing, very close view. Everything is at 25 meter spacing. And so many instruments were installed. Say 2000 settlement markers, 100 vibrating wire piezometers, a large number of instrumentation was done. Okay. So the whole thing is around 90 hectares or 100 hectares. Area is around 100 hectares. Now look at this. This is only that 1 kilometer by half a kilometer container yard. So much of instrumentation is there. Now what we did some back analysis using curve fitting method. So first is alpha method. Look at this. These are these extensometers by curve fitting from theoretical prediction. So we have theoretical prediction is the back analysis is that black line. Others are all extensometer data. So this is from extensometer data, settlement gauge data. So we got CH of around 3.75 to 4 meters square per year from this, with an S of 2.5 and KH and by KS of 3 to 4. Then we did alpha method. This is from Hansbo's equation from alpha method. Here again we got CH of around 1.8 to 4.7 with S of 2.5 and KH by KS of 4. So another using extensometers, we get CH of around 3.7 meters square per year. Then other back analysis using settlement gauges. So CH was around 4.7, S of 2, KH by KS of S. So we tried to fit it with the actual monitored curve and then found out what are those values. So now look at this range of CH values. So estimated CH was 2 to 2.42 from radiant consolidation test. From field cone dissipation test, 2.5 to 5.2. Then based on back analysis, based on curve fitting, we got 3.75 to 4. And based on alpha method, we got 3.42 to 4.7. The smear ratio, diameter ratio was 2 to 2.5. Smear permeability ratio was 3 to 4. And then the indicating smear, suppose smear was there, then the CH value was 1.6 to 2. So there was some smear where the thickness of clay was very high. Where the thickness of clay was less, smear was not there. This is the finished surface, which was handed over to the client. This is the building that was constructed. These are the railway tracks. Okay, so that is how. I will just show you one short video. I'll get out of this and then share that video. AECOM was the detailed design consultant for the contractor ITD cementation for BMCT project at JNPT, Navi Mumbai. The reclamation is the largest in the country, which is around 100 hectares. There were a myriad of challenges that were faced during execution.
The subsoil profile below seabed level comprised of 4 to 18 meter of very soft clay. You could imagine the top 5 meter was as soft as butter. Above this, a finished reclamation land must be created for the container yard and railroad corridor.
The greatest geotechnical challenge for Chennai team was to give the most simple but robust ground improvement scheme by installing PVDs that could be executed by a local contractor.
Slope stability analysis and deformation analysis were carried out. The entire project was completed within 27 months with elaborate instrumentation and monitoring.
We are proud to say that the project was executed to the utmost satisfaction of BMCT. I am sure my team would agree that this is one of the most fascinating projects for any geotechnical engineer. We are not doing research over here. So that is why the most, as Jimmy said, no, we will be extremely conservative, and because time is the essence over here. So we took the worst CV parameters, may not be the worst, but as I told you, 25 percentile line. So everybody is happy that it is not too conservative, it is not too optimistic also. So that is how we go about it. Okay, so for this, you please refer to Professor Madhav's Geo Sutra. How these get over consolidated, there has now been deposition and erosion and all has not taken place over here. How the over consolidation happened over here? All this is because of the wetting and drying process. So that is a new type of approach which he has given. So you can read that. Then if over consolidated clay, the Skempton's PI versus chart is used for grain size strength calculation is not correct. The relationship formula is for correct. Ultimately, we are doing instrumentation and monitoring and then do a we need some way to start. So we started with this and then we monitor. Everything is through instrumentation. Everything is through measurement only. So the designs may be for the starting stage. That's why I answered that that is the starting point, and then everything is through monitoring only. Ultimately, what I need is 95% consolidation and whether I have achieved my shear strength to go to the next stage. So I will wait further. So some places where the thickness of clay was high, although my predicted time for 95% consolidation was 3 months, it went beyond even 6 months. Certain places, 5 months, 6 months. Certain places it was less than 3 months where the thickness of clay was less. Oh, dam grouting. All this is for very short, small areas within boreholes and all. Now we are talking about 90 hectares. There were initially proposals for deep soil freezing, deep soil grouting and all, but those are too expensive and how much we don't have, and this is going to stay for a few 100 years, how it will behave. So the easiest and best method, tested method is to using PVD only. All this you can use at a smaller site where the area of treatment is less.